While I was preparing to do part 3 of my X.509 series, I got sidetracked into doing a talk for a DevSecOps group on X.509 certificates. So this is that talk. It's more technical than my series was. It covers some of the technical details that I gloss over, and it's probably of more practical value to people who are managing X.509 certificates in a DevSecOps environment. Welcome to Managing X.509 Certificates in Your Environment. I put this together because a lot of organizations are adding TLS to their infrastructure. There's a lot of confusion about the role X.509 certificates play and how to effectively employ them in your architecture. When you ask most people why they should use TLS, they'll tell you it's to encrypt their data in transit. So let's first talk about encryption. Most cryptography uses symmetric keys. Symmetric key encryption uses the same key to encrypt and decrypt the data. That means you need to exchange a secret key, which means that both ends of the secure communication need to have a pre-existing relationship. The key technology for modern secure connections is asymmetric cryptography. Asymmetric cryptography has a key pair. With a key pair, you designate one as your private key, and you keep it secret, and the other is designated as the public key, and you can send it to anyone. With asymmetric encryption, you need both keys to go from plain text to ciphertext and then back to plain text. This way, if you have a key pair, you can send the public key to an unknown party, and this allows them to initiate secure communication between the two endpoints, even if you have no prior relationship. But you don't need an X.509 certificate for this. In fact, SSH, or Secure Shell, sets up a secure connection using an ephemeral key, a key pair created just for the session. And since version 1.1, TLS sets up the encrypted connection with an ephemeral key pair. So what's the X.509 certificate even for at this point? It's for authentication. An X.509 certificate attaches an identity to a key pair by incorporating the public key to create an attestation of this pairing. Originally, this was intended to identify users, but it ended up being used most often to identify servers. There are still client certificates, of course, and we'll call both client and certificates entity certificates. All other certificates are CA certificates that are used to sign entity certificates. Most of our experience with connecting to servers using TLS is when we're conducting e-commerce. In this case, it's also really important to be confident that we're talking to the correct server. When we're managing private networks, like our development systems, pipelines, and the parts of our deployments inside the firewall, a lot of organizations just use unencrypted connections. But more and more we're using TLS, and people tend to think of this in terms of encryption. So they do as little as possible to enable it. This usually means using self-signed certificates or using the same certificate for every endpoint. This removes the endpoint authentication feature of TLS, but that feature is important, and there's an emerging best practice that's making the endpoint authentication mandatory. This best practice is Zero Trust Architecture, or ZTA. To sum up what that is, ZTA is trust nothing, verify everything. Trust nothing means that you can't trust that your network is secure. You also can't tell that the server on the other end of your connection is legitimate. TLS solves both of these problems by keeping your network traffic secret, but also forcing your server endpoints to identify themselves. This means that you need to deploy your microservices and CI/CD tools with TLS enabled. It also means configuring these endpoints with proper X.509 certificates. A lot of people know how to install X.509 certificates, but not how to manage them in the enterprise. So I'm going to talk about understanding what the X.509 certificate is and how to manage them effectively. A lot of tools these days don't even let you install without TLS. They'll come with default certificates in case you don't have any, or maybe you create a few certificates to throw onto your servers. Then you get your first developer complaint. Hey, I can't connect to GitLab anymore, and then they show you this error. Soon, everyone is looking up the turn TLS errors off option for their tools. This is when people start adding -K to their curls or trusted host to their pip install or whatever they need on their other tools. In fact, here's an example of settings that result in completely ignoring everything about the server certificate, including expiration. Now you have TLS and you have certificates because you can't deploy TLS without certificates, but you're violating zero trust architecture because your clients always trust and never verify. So let's start to fix that. The first problem is that your internally generated certificates are not going to be signed by a, quote, well-known CA, nor should they. This is what the error on the previous slide was complaining about. The reason why the client trusts the server certificate is that it's signed by a trusted CA. A lot of time, people create self-signed certificates for an entity, and this may be rejected by TLS verification. If an entity certificate is self-signed, it can't be verified. If the self-signed certificate is marked as a CA certificate, that's actually normal. CA root certificates are self-signed, but then it shouldn't be used as an entity certificate. If you try to add your self-signed certificate to a trust store and it's not flagged as a CA certificate, it may not be recognized as a trust anchor. So TLDR, don't do that. I think most people know that they should create CA signing certificates and use that to generate server certificates or entity certificates. If we trust a certificate because a particular CA signed it, how do we know to trust that CA? And the short answer is we just do. The long answer is that the CA certificate has to be preloaded into a trust store on the client. This is why we sometimes refer to the CA root certificates as trust anchors. This means that if you have a private root certificate, you need to add it to the trust stores on all of your client systems. On Windows, there's a standard place to put CA root certificates. On Linux, there can be multiple places. For example, if you want Docker CLI to trust the CA of your private image registry, you'll need to put the CA certificate in here. Other places you might need to put it are here or here. And this is on Ubuntu. There are other places on Red Hat. Chances are that after an initial round of deploying your root certificates everywhere you can find, you'll be finding more places that it needs to be over time. For example, if you create a new workstation or spin up a new cluster or bring in a new technology that has its own trust store. For this reason, put the CA certificate somewhere easy to find, like a file share or a Git repo. Some people seem to think that the CA certificate is some kind of carefully guarded secret, but that's the exact opposite of the case. The private key associated with the CA certificate should be a closely guarded secret, but the public portion is, again, public. I've kind of jumped around a bit here, so let's review what the TLS stack is going to do to verify an entity certificate. The whole reason that you distribute the certificate for the root CA is so that the client TLS stack can validate the signature on the server certificate. The server certificate will specify an issuer. This is the name of the CA certificate that signed it. The distinguished name attribute, or the DN, of the signing certificate must match the name of the issuer attribute of the signed certificate. Then TLS will validate the signature on the certificate using the public key in the CA certificate. If this was an intermediate CA certificate, it continues up the chain until it gets to the root. Root CA certificates are self-signed, and they are only trusted because they're preloaded on the client. Next, the server certificate needs to have a name that matches the host portion of the URL. If you have a GitLab server at gitlab.internal, it should have a certificate with the name gitlab.internal. You can use wildcards so that a certificate can match a group of servers, but whatever you do, do not wildcard your entire domain. The purpose of the X.509 certificate is establishing trust and that you are talking to the intended server endpoint. The more specific the certificate name, the stronger the trust. If you have internal components like a private GitLab, a private SonarQube, or Artifactory, you should create specific certificates for each one. Originally, the server name was just what was in the common name of the certificate. There are some issues with that, so now the name is matched against the subject alternate name, or SAN attribute. The common name is only used if the certificate doesn't have a SAN or the SAN is marked not critical. The biggest advantage of the SAN is that each entry has a type. For server names, there are DNS and IP address entry types. A DNS entry must be a proper DNS name, and it can start with a wildcard. An IP address entry must be a proper fixed IPv4 or IPv6 address. This allows a certificate to be valid for a bunch of different servers or a bunch of different ways of addressing the same server. Again, for an internally used certificate, specificity is more secure. For external certificates, you're just trying to get the browser to be happy so you can do whatever you want. Now, this Google certificate matches a lot of DNS names, and you can only see part of a very long list here. Note that this SAN is marked not critical. This means that there's a valid CN attribute that can be used. For your internal server certificates, omit the CN and mark your SAN critical. For client certificates, have a distinguished name and possibly omit the SAN. The SAN has some attribute types that are useful for users or clients, such as email address. So you can use those, but mark the SAN as not critical. Moving on, another validation that you may know is validity dates. There's a not before date and a not after date. As the names imply, the certificate is not valid until the not before date and is no longer valid after the not after date. We'll talk about validity date policies later. Here, the not before date is being called issued on, and that makes sense because this date should never be in the future. In other words, the latest date that it should be in the not before date is the date the certificate was issued. And here the not after date is called expires on. But in the actual X.509 standard, they're called not before and not after. The X.509 standard defines key usage and extended key usage. The key in the certificate is associated with an identity in the certificate, and the key usage attributes explain what you can do with the key with respect to the identity. So key usage was the original set of key usage attributes, and these are the ones that you should know about. There's digital signature. That should be set true for any key that can be used in verifying of digital signatures or digital signing in general. The key cert sign, this allows this key to be used to sign other certificates, and that should be set true for any CA certificate. And the CRL sign allows signing of certificate revocation lists. This was the original way that you could distribute a list of certificates that were revoked. They were still valid in every other way, but they were revoked and therefore no longer valid. So you get a certificate revocation list. And because when you're getting a certificate revocation list, you don't want to have to worry about the certificates required to get it, you would usually get that CRL over plain text, and the CRL itself would be signed instead of going through a validated connection. So later they added extended key usage, which added some more specific qualifiers to what you could do with the certificate key. So there's server auth, which is specifically for certificates that are used to authenticate server endpoints. There's client auth. Those are certificates that are used specifically for identifying client endpoints. There's code signing. So if you use a technology like Java, for example, that allows for code signing, you need that thing set to true. Email protection is specifically for SMIME and other email privacy and protection technologies. Then there's OCSP signing. OCSP is a protocol that replaced CRL is a more efficient way of checking for certificate revocation. Again, OCSP is often done over clear text. It's the responses themselves that are signed for validation purposes. In case you hadn't figured this out, you're going to want to run your own certificate authority to create internal certificates. You can actually create all the certificates you need using the OpenSSL on the command line, but there's more to it than that. So you should really use a tool that will give you some management capabilities. If you have 2 servers, you can probably manage them ad hoc. But when your PKI grows, you're going to get swamped, and you don't want to have to retool during a period of growth. So run your CA like you have 10 times the scope. If you have 2 servers, run it like you have 20. If you have 10 servers, run it like you have 100, and so forth. A management tool is also going to give you the capabilities beyond just creating certificates. For example, you'll need to track the certificates you've issued. More importantly, you need to be able to revoke certificates. Those revocations should be available to clients in the form of a certificate revocation list, a CRL, and an online certificate status protocol, OCSP endpoint. Without those, you won't be able to effectively revoke the certificates, which is part of your PKI security. Advanced tools may also support the Automatic Certificate Management Environment, or ACME standards. This allows for the automated issuance of certificates. If you're getting into automating your PKI, then you have mastered certificate management. If you haven't mastered certificate management, don't do that. Okay, so your first order of business is to create a root certificate. This is going to be the certificate that you will need to copy everywhere. For that reason, you'll probably want to give it a long validity period. You can use this certificate to sign all your entity certificates, or you can use this certificate to create an intermediate signing certificate to sign your entity certificates. What are the pros and cons? Everyone understands that a server has to send its certificate down to the client. What a lot of people don't know is that it also has to send any intermediate certificates as well. So all the certificates that are circled in green on this diagram need to be sent down from the server. The root certificate is not sent because it needs to already be on the client. If you don't send the intermediate certificates from the server, then the client can't properly validate the server because it may not already have copies of the intermediate certificates like it has copies of the Trust Anchor root certificate. Implementing this is pretty easy. When you point your server to the certificate file, it's actually a file with all the certificates in the chain, but not the root. If you've ever set up a server, you probably had a certificate file and then the private key file. So in this case, you'd have a certificate bundle and then the private key file for the server certificate. Because the intermediate certificates must be distributed with the server certificates that they sign, this creates additional certificate management overhead. So for this reason, you might want to avoid using an intermediate certificate. A lot of organizations use intermediate certificates in order to break up their job of managing a massive PKI. If your infrastructure is fairly small, then you won't need that. But a more salient reason to have an intermediate certificate is to protect your root certificate. In fact, the Small Steps certificate management tool forces you to do this. After you create the intermediate certificate, then you take the private key for the root certificate offline where it can't be stolen by a network intruder. Now, this is a great practice, but having an online root certificate that signs everything might be secure enough for your needs. Finally, your root CA can be given a very long validity period because it's very secure, and your intermediate certificate can be given a much shorter life. And since it's the root certificate that you're going to want to distribute everywhere, that's going to save you headache later. So the primary thing that distinguishes between a CA certificate and a non-CA certificate is the basic constraints attributes, which it has 2 fields. The first is the CA field. CA certificates must have this set to true. They also need the key cert sign key usage flag set as well. If the basic constraints and key usage don't match, the TLS stack may reject the certificate. So at the very least, you need one configuration for CA certificates and one for non-CA certificates. Again, the more specific you tailor the certificate features, the more secure your PKI. A self-signed certificate with CA equals true is a trust anchor or a root certificate. Otherwise, if CA equals true, it's an intermediate CA certificate. The other field is an optional path length constraint. This controls the depth of the trust chain you're allowed to build. A certificate with no path length constraint has no path length constraint. This means there's no limit on the depth of the trust chain, so you can have intermediate certificates as long as you want. Don't do that. Set the path length constraint on the certificate to 0 for the certificate that you use to sign entity certificates. If it's an intermediate certificate, then your root certificate should have a path length constraint of 1. So set the path length constraint explicitly. Okay, so now we're going to create our private CA. What should we use? Well, there's a lot of products. Here's a couple that are with a free tier that are recommended. CFSSL is from Cloudflare, and it's mostly command line stuff. And then Small Step CA or Step CA has a free tier that has everything you need for a modest size PKI. Small Step is also super easy to set up, so it might be the best open source choice if you're new to certificate management. It's going to force you to have an intermediate signing certificate and take your root certificate offline, but you should be doing that anyway. But don't fire these up right yet, because there's a few more things to cover. First, I want to talk about certificate expiration. When a certificate expires, it has to be replaced. Once the CA generates a new certificate, it needs to be deployed in place of the expiring certificate. So you need to make that deployment part of your infrastructure as code or your configuration as code. So you can just drop the certificate into an S3 bucket or a Git repo or have it installed where it needs to go. Having intermediate signing certificates can double this management burden. Obviously, you have to install a new server certificate when that is expiring. But remember, the server also has a copy of the intermediate certificate, and the server certificate also can't technically be valid longer than the intermediate signing certificate is valid. So when the intermediate signing certificate expires, it also needs to be replaced along with a new server certificate signed by the replacement CA certificate. The likelihood that these two expirations are always going to be synchronized is very low unless you run a frequently segmented PKI. So what you're going to see is here's the expiration time. So all of these dotted lines represent times where you're going to have to, renew the certificates on a server. Here's my recommendation for how to set things up to stay secure and minimize the management overhead. First, we create a root certificate. Let's give that a 10-year lifespan. 10 years is practically forever on an IT project. Next, we're going to create an intermediate signing certificate. Now we can take our long-lived root certificate offline so it stays as secure as possible. This intermediate certificate will have a lifespan of 2 years. Now here's the trick. We'll create a replacement after 1 year, then we'll create the next intermediate CA certificate a year after that, and so on. We'll call the first 3 A, B, and C. The intermediate certificate will be used to sign entity certificates. The entities should have a lifespan of 1 year. During the first year, we sign server certificates with intermediate A. Then after that, we sign certificates with intermediate B. And then a year after that, we sign them with intermediate C, and so forth. That means when the certificate that was signed by intermediate A expires, we'll be signing the replacement with intermediate B. So essentially, we'll be replacing a bundle of intermediate A with the expiring server certificate with a bundle of intermediate B and the new server certificate. And then a year after that, we'll replace that expiring certificate with a bundle of intermediate C and a new server certificate. And by doing this, you can see that we have greatly reduce the number of certificate deployments that we need to perform. You don't have to use a 1-year entity lifespan. You could make it 2 years or 18 months. Just keep the 2-to-1 lifespan ratio. You can also make it shorter than a year. This Google certificate we looked at previously has a lifetime of only 12 weeks. Now, this certificate is sent to the public internet, so the risk of being compromised is higher. It's also a Google certificate, so it's a high-value target. So there are likely nation-state level actors that are trying to crack this certificate. So 12 weeks greatly reduces the risk of that happening. But how much risk you're willing to accept should dictate the lifespan of your entity certificate. So if you're really worried about your certificates being compromised on your internal network, make your lifespan 12 weeks. But 1 year is the current default best practice. So who's ready to issue some certificates? Let's review where we are. Okay, we've picked out and set up our certificate management software. We have a plan to distribute the certificates to where they need to go. This includes infrastructure as code, configuration as code, and our deployment pipelines. And we have a policy for certificate expiration. And now we're ready to start issuing certificates, right? No, not yet. We need to talk about public key infrastructure, or PKI. So issuing certificates is just one part of a public key infrastructure. The management tool that you select doesn't create a PKI, it just enables it. What constitutes a PKI is a combination of policy and procedure. Here's a diagram of a basic PKI. In the lower left, you can see a developer who generates a certificate signing request, or a CSR. A CSR contains a public key and an identity. The connection between this public key and the identity is ultimately what the CA is going to certify. They send the CSR to a registration authority, or RA. Could be sent via email, could be sent via S3 bucket or on a thumb drive. The submission mechanism doesn't have to be particularly secure because the RA will perform vetting on it. The RA is a function performed by at least one person. The RA needs to verify that the request is legitimate. For example, is the identity information valid? Does it meet the requirements of your organization, such as how deep you can put the wildcard in a DNS name? Does the person requesting the certificate have the authority to control a certificate for that server identity? If you have a small organization, this might be a really easy job, but it's an important job, and it can't be done by the same people or person who performs the CA function, the certificate authority function. In security terms, this is a separation of duty. It's critical in reducing fraud, errors, misuse of information, and insider threats. But more practically, the RA provides a necessary quality gate to keep the CA from having to deal with spurious certificate requests. But even if you have a small organization and a small PKI, find different people to perform the CA and RA roles. So once the RA has approved the CSR, they send it to the CA. The CA signs it with the appropriate CA certificate, and the signed certificate is delivered to the requester. This delivery doesn't have to be particularly secure either, because the signed certificate is not a secret. The private key is, but the requester didn't send that to the CA, and then, in fact, they shouldn't send it to anyone. The requester can now install the signed certificate and the associated private key onto the server. The final desk on this diagram is the validation authority. This is where systems can go to check to see if an otherwise valid certificate has been revoked. This is part of your CA tool, which should serve OCSP requests and provide CRLs to systems that request it. You need to keep your CA system protected, but the OCSP and CRL endpoints must be visible to the clients who are validating the certificates that you issue. So while we're on the subject of sending certificates around, let me cover file formats. You've probably seen a few different extensions on certificate files: PEM, DIR, CIR, and CERT. What are in these? So first of all, there are only two formats for X.509 certificates: DIR and PEM. The CIR and CERT file extensions don't really mean anything and can be applied to either file format. The important thing is that those file extensions are not used for a file that contains both the certificate and the private key. So the X.509 specification defines the contents of an X.509 certificate using Abstract Syntax Notation 1, or ASN.1. ASN.1 is just a data schema that defines a data structure with named and typed fields. It doesn't have a digital representation. So you could represent an X.509 certificate as XML or JSON, but neither of these standards existed until over a decade after the X.509 certificate standard was created. So instead, we got the native format for X.509 certificates as Distinguished Encoding Rules, or DIR. PEM stands for Privacy Enhanced Mail. This was the name of an early 1990s project aimed at improving email security. Part of that system required you to be able to email certificate images to other users. Now, SMTP didn't handle binary data at the time, and it still doesn't handle it very well. So they did with what all email systems still do. They converted the binary to base 64. It wasn't just that. You also put a couple of lines around the base 64 indicating that that data is a certificate. But bottom line is the PEM file is just the DIR file base 64 encoded. That's all it is. Sometimes you want to have one file with both the certificates and the key. You should always encrypt the key in this case. If it's to be installed in a server, you can separate the key and store it unencrypted in the server configuration later. But the private key encryption is standardized under the public key cryptography standards as PKCS number 8. So the DIR file format will only contain the certificate. This is because it is a digital representation of the certificate and the private key is not part of the certificate. Because the PEM file is just delimited text, as we saw earlier, talking about certificate bundles, you can put multiple PEM encoded items into a PEM file. So you can put the certificate in there, and then you can put the private key in there with it. So a PEM file frequently, or at least sometimes, contains the certificate and the private key bundled together. Finally, PKCS number 12 defines a container file format that can be used to send certificates, keys, or both. It can also include metadata like a friendly name for the certificate and other attributes that aren't actually in the certificate itself. It's primarily used for transferring certificates from one place to another. Oh, and you'll see those as P12 and PFX files. Before I leave this topic, I just want you to note that you can print out PEM files. They're just text. So if you want to store offline backups of your certificates or your keys, printing the PEM file is actually a good way to ensure they'll be readable when you need them. Most removable media can be corrupted and lose data, but paper is actually pretty robust unless you have a fire. We've covered pretty much everything now, but there's still one more thing you need to do to prepare your CA to be part of a PKI. We've talked about how the RA enforces the rules around getting a certificate from the CA. The people in your organization need to know those rules. They also need to know who the RA is and how to send a request to the RA. They might need instructions on how to generate a CSR. They need to be told how to specify the subject alternate names and what those should be. If you're issuing client certificates, you need to ensure that the subject name is correct. You'll need rules about how the common name is formatted. For example, is it just written out as family name, comma, given name? What values do you expect for organizational unit and the other distinguished name components? Do you include email address in the subject alternate name? Is it mandatory? All of this information needs to be decided, written down, and made available to the PKI team as well as all the people who need to obtain certificates. Think of it as an informational booklet. So now that you've documented your policies and procedure, now you're ready to start certifying. So I'm just going to end on this one last slide with reference of some of the do's and don'ts that we covered in here. When I gave this talk to this DevSecOps meetup, we had a really good discussion afterwards about some of the details that I glossed over. And I was thinking about going over those here and tacking on a section where I walk through them. But instead, I'm going to make a series of much shorter videos covering those questions. So I hope to see you there.